Okay, exam on Wednesday, so I'm presuming everyone's listening to me now. Okay, presumably everyone had a good weekend. As you go into the exam for Wednesday, presumably this will work. There we go. I typically do not do this, but you guys have actually done really, really well for your first two midterms. So whatever you're doing to prepare for them, it's working. Okay, so keep it up. And this is a list of topics for Wednesday's exam. Presumably you guys realize from looking at it, it's everything. But it should help. So as you go into Wednesday's exam, I do want you guys to feel a little confident, not overconfident, but a little confident because you're doing well. This exam is a little easier on the math side, but it is harder conceptually, right? So pay attention to the clicker questions that were in the previous lectures and just do the concepts a little bit later when you're a little bit more awake. As before, you can start at 7:30 and good luck. Other announcements. There will be no homework this week or pre-lecture for next Monday. Simply because the topic is going to be a continuation of today. The following week, Thanksgiving week, Monday, of course, there is a lecture, and I do want you guys to attend because it is one of the most important lectures of this semester, apart from a cool demo. Today's demo will be cool for me because you're going to do it. But, okay, so let's focus now on waves, and remember, I will see you guys on Wednesday for the exam, and on Monday for the next lecture. And then after that, of course, it'll go back to the nice sequence of homeworks and pre-lectures and more fun. Okay, so the topic for today is waves. And waves is an interesting topic to introduce today because it is intrinsically linked to something you're going to be tested on Wednesday, simple harmonic motion. Right? So a lot of the stuff we're covering today is actually a reiteration of stuff you already know. Well, stuff that you will be tested on Wednesday. Not waves per se, but oscillations is on the exam. Right, so the question becomes, what is a wave? Right? So this is where the demo comes up, which you guys are going to do. I believe the PATS 1, I had to ask someone because I don't really follow this. But this can be thought of as a stadium. This idea is essentially stadium seating. Does anyone know what a wave is when we talk about people doing a wave in football? Great, so everyone can please stand. Make sure no one's around you. Everyone should be standing. I can actually see you. Right, make sure no one's around you. I do not want you thwacking anyone at 8 in the morning. You're going to do a wave starting from there to there, and I'm going to judge how good this wave is. So, do it. On the count of 3, from that side to that side, right? With your hands, right, up and down. So 1, 2, 3, go. Now go the other way. 1, 2, 3, go. Okay. Right, sit back down. Now, everyone's awake, right? That was kind of the point of that. And this is what you did. That's what a wave is, right? It's something that traveled from there to there, right? And then back from there to there. Right? But what was the actual motion that you all did? When you moved, what did you do? Did you move this way or did you move this way? You moved up and down, right? And whatever this thing was, right, this wave that traveled, it went from there to there. Correct? So, if I were to ask you what was the direction of your motion, right, compared to the direction of the wave, is the answer parallel or perpendicular? Were you moving perpendicular to the way the wave was moving, or were you moving parallel to the way the wave was moving? Perpendicular, right? Correct? Parallel would be like you all stand up and sway, right? We're not going to do that. That kind of leads to people sleeping or bumping. But a transverse wave is what you did, right? So there's basically two kinds of waves. There is a third that's kind of a mix, right? But a transverse wave is a wave that's defined as the direction of the oscillation, right? If you just stood up and did this with your hands, right? Your hands are oscillating, correct? The direction of the oscillation in the medium, and in that case you were the medium, right, was perpendicular to the direction of propagation of the wave. Right? Those kinds of waves are called transverse waves. Everyone with me? Okay. The other kind of wave is this. Right? In this case, the direction of the oscillation is parallel to the direction in which the wave is propagating, right? So this wave is going like this. Right? And every single particle in this is oscillating like this. Everyone following that? Right? So the direction in which the medium is oscillating is actually parallel to the direction in which the wave is propagating. Right? Those kinds of waves are called longitudinal waves. Okay? And then you have what's called a combination. It's a surface wave. So this is more like you have a nice calm lake, and when people see a nice calm lake, they can't really help themselves. They start chucking stuff in it. And they set up waves, right, on the surface. Right? And if you look at those surface waves, they're doing this. They're moving both side to side, right, and up and down. Right? That combination is a surface wave. So it's a combined longitudinal and transverse wave. Okay? Right, so these are your standard examples. Your transverse wave doesn't really count as so much of a physicsy transverse wave. The more physicsy representation of a transverse wave is a wave on a string. Right? You stretch a string and you pluck it. Right? The string oscillates like this, and the wave propagates in a certain direction. Right? That is a transverse wave. Does everyone know what a slinky is? If you don't, Google it. You'll get some funny videos. Right. So if you set up a wave in a slinky, right, every single part of the slinky is oscillating parallel to the direction in which this wave is traveling. Right? So that makes it a longitudinal wave. Everyone following me so far? Now comes the fun question. What's actually traveling? And I'm not asking this clicker question, which, by the way, is a good thing. Okay, clicker questions are not anonymous unless I make them anonymous. A whole bunch of you staring at me can yell out an answer, and I have no idea who said what. Right? You have the advantage of the anonymity of numbers. Right? So someone take a wild guess. What's actually traveling in a wave? What goes from there to there? Obviously, no person did. Right? When you set up a wave that went from there to there, none of you actually moved from there to there. Correct? The same thing is true on a lake, right? Let's say there's a bunch of leaves on the surface of a lake, right? And you toss a pebble into it and you set up surface waves, right? Unless your aim is really, really good, the leaf is not really going to come very far towards the surface, towards the shore. Right? It's just going to kind of oscillate about where it is. Correct? It's not actually moving all the way to the shore. Right? So when a wave travels from one place to the other, it's not the medium that's actually going from one place to the other. Everyone following that? So what is? What's going from there to there? Sorry? Energy. Very good. Right? There are only two ways we know of how to take energy from one position and take it somewhere else. Right? The first way is the one you've been studying since the beginning of the semester pretty much. Right? You take a particle that's moving with a certain speed, and as it goes from there to there, right, its kinetic energy went from there to there. Right? But waves are another way to get energy from one place to another, and in this case, no matter actually moves from one place to another. Right? All that's transmitted is the wave. Correct? So when we talk about the direction a wave is traveling, what we mean is the direction in which energy in that wave is traveling. Okay? So waves are a disturbance in space and time, right, that propagate. And what actually propagates in a wave is the energy, right? The actual motion of the medium itself is simple harmonic, right? It's an oscillation. Everyone following me? Right? So the simple harmonic motion that you studied last week, that's what each part of the media is doing. Right? It's oscillating about an equilibrium. It's not actually going anywhere. Right? But when it does this, the energy is transmitted from one place to another. Everyone with me? Okay, so fundamentally, waves transport energy from one place to another place. Okay, so let's see if you guys are still awake. And the way I'm going to do this is I'm not really going to look at what you guys are saying till at least a good fraction of you have said it. So I have a long metal rod, and for some reason I take a hammer and thwack one end of it. What kind of wave travels along the rod? So remember, if you're asked what kind of wave, what you want to think about, what's the direction of the energy, right? Where is it going? Along a rod, it's traveling along the length of the rod. Right? So if I've thwacked the rod like that, are the molecules in that rod oscillating like this or like this? Like this, right? So this oscillation, the direction of this oscillation is along this line. Right? This line is parallel to the line along which energy is propagating. Correct? That makes it what kind of wave? Longitude. Everyone with me? Okay, I did promise I won't answer this before you answered it, and I just did. Okay, very good. Let's do this one. It's a wave on a string. Think of a taut, stretched string, like along a guitar, and you pluck it. Okay, click something, and let's see where we are. Very good. Okay, so we can identify longitudinal and transverse waves. And the idea is that all kinds of traveling waves, right? Waves that travel from one place to another, take energy from one place to another. Okay, so far, what we have is a wave is a disturbance that's propagating through space and time. Right? So what we mean when we say it's a disturbance is it's an oscillation, right? Stuff is oscillating, it's attached to other stuff, right? So if something starts oscillating, this other stuff that's attached to it starts oscillating, right? Think of holding a book and you sway side to side. The book is going to sway side to side with you. Correct? If a bunch of you stood up and held hands and someone yanked from one direction to the other, right? The other person is being yanked. Correct? So they're linked to each other. So the propagation is because they're linked. Right? If instead of a simple pluck, right, I decided to take a piece of string and just oscillate back and forth, right, then all that means is now continuously sending energy down. Right? A single pluck is like a single pulse of energy, right, that goes from there to there and it's done. Right? If I keep shaking it. Right? I'm continuously putting energy into the system so that energy will keep traveling. Everyone with me? Right? So there's no real difference between a single pulse and multiple pulses. Right? The only thing is multiple pulses, you're continuously sending a pulse. Right? Okay. Now, you can find how a wave, the position of the wave varies with position. So most waves are sinusoidal in space and time. Right? That's what a physicist would say. And that's why I said that. What that means, of course, is when we say something is sinusoidal in space or something is a function of space, right? What we mean is take a picture of it. Fix time. Right? So if you fix time, right, you're literally taking a photograph, right, and studying how something changes as a function of space, which is position. Correct? So if I have a wave on a string and I pluck it, right, and I take a picture of it, right, I am seeing how that wave varies with position. Everyone with me? Right? So it's taking a picture of it. If I did that, so I'm plotting displacement of the medium on the y-axis, right, and I'm plotting position on the x-axis. Everyone with me? Right? So this is taking a picture of the wave at one instant in time. Right? And if you do that, it looks sinusoidal. Everyone following me so far? Okay. The other aspect of waves is they are sinusoidal in space and time. So this is the math for this. Don't worry about it. You don't need to know the math. But essentially, know it's a sinusoidal function. So it's a sine or a cosine. Now, the other thing you can do is instead of taking a picture of it, right, which is looking at it as a function of space, if you want to look at something as a function of time, right, you fix the point in space and you let time vary. Right? So in the previous case, you're looking at all different parts of that string, right, as they're varying as a function of space. Now look at one part of the string and vary time. If you look at just one little portion of that string, it's going to be doing this. Right? It's going to be oscillating. And if I plot that as a function of time, right, this is something I expect you guys to be able to do on Wednesday. Plot the oscillation of a particle as a function of time. Right? It's going to look like this. Right? Looks exactly the same as it did for space, by the way. Right? So that's what we mean when we say a wave is an oscillation in space and time. Right? The space part is a little new, but the time part you've seen. Right? It's just the medium oscillating about an equilibrium position as a function of time. And for that, you can define a time period. Right? The time period is the time taken for one complete cycle. Everyone with me? And from that time period, you can define a frequency. Right? So waves have a frequency. Right? There's a number of cycles per second. Everyone following this so far? So, we have two kinds of sinusoidal variation, right? And pay attention to the axes. So, if I take a picture of the wave as a function of space, that means fixed time, this axis is position, right? Measured in SI units of position or, remember the anonymous answer that can be yelled out, what are the SI units of position? Meters, right? It's length. And this is displacement, again measured in meters, right? So when you take a picture of something, you pick a picture of the wave, you get a wave looking like this, and pardon my drawing, right? It looks something like that. This is one complete cycle. Everyone agree? Peak to peak. Okay? And this distance is actually a distance. It's a length. Right? It's a physical length, the length of this oscillation. Everyone following that? That is called the wavelength of this wave. Okay? So this is lambda. So lambda, pronounced, it's Greek as usual, right, is the wavelength. Okay, similarly, a wave is sinusoidal in space and time, right? So this is the amplitude, and this is now time. So this wave looks like this is a function of time, right? So this now is a length of time, right? Just like it was last week, right? And we call that the period of the oscillation. Everyone following me so far? Right? So in order to determine whether you can find the wavelength or the period, look at what you're given. Right? If you're given the wave as a function of space, you can find the wavelength. Right? Because that peak to peak is now length. Right? That's the length of the wave. If you're given the wave as a function of time, you can find the period. Right? Because peak to peak is now time. Everyone following me? Okay, so we can define a frequency for the wave, which is 1 over t, right? And f is 1 over t measured in hertz, and t is measured in seconds, and we will all see this again on Wednesday. Okay, so now that becomes the period. So this is your position versus position. So it's the amplitude versus position, right? So that length from there to there will be what? Wavelength or period? Wavelength. Good. Okay, wave characteristics, right? So if I have a wave going from one place to another, right, what properties of the wave are important? How do I describe one wave with respect to another wave? What's the difference, right? So wavelength is one difference. Waves can have different wavelengths, right? The frequency is another difference, right? And they're linked, okay? And the link is fundamental. So there's no acceleration in any of this, right? The energy is traveling at a constant speed, correct? Right? The energy goes from one end to the other end at some fixed speed, the speed at which it propagates in a medium, right? If I were to ask you, in one cycle, right, how far did the wave go? What's the answer? Sorry? No? How far does the energy travel in one cycle? The wavelength distance. Correct? Right? In one cycle, the energy has traveled one wavelength. Right? And the length of one cycle is the period, right? So it's the time. So the speed is lambda divided by the period, like lambda over t. Yes? Right? And 1 over t is frequency. Right? So the speed of a wave is lambda times frequency. Okay? If you forget everything else from this entire semester and plan to take general physics 2, please remember that part. Okay, V is lambda times F. Okay, let's understand this equation a little bit. The dependencies in this equation require a little bit of thought. Okay, my standard example for this, and this still kind of sadly works. I depend on my mother, right, for a lot of things, unfortunately. She does not quite depend on me. Okay, so when we're analyzing dependencies, right, so if you look at that equation, V equals lambda F, right, one is tempted to say that if you change lambda, you change V, right, that lambda is related to V, right, according to that expression, F is related to V according to that expression, right, so if I start changing stuff, stuff should change, correct? That's a little, that's not actually quite correct, right? It's a dependency of what depends on what doesn't imply that everything else changes, right? So what I mean is the wavelength does depend on the speed, but the speed doesn't depend on the wavelength. Can someone tell me what the speed of a wave should depend on? And this is a hard question. If I'm talking about a wave propagating in a medium, what should that speed depend on? And to answer that, right, when you think about it, it depends on whatever's pulling this thing back to its equilibrium. Right? Like if you have a stretched string, okay, and you pluck it, it matters how tightly stretched that string was, right, in order to determine how fast energy travels. Correct? So what we're saying is that the speed of the wave depends on what? The medium itself. Right? It depends on what the wave is traveling in. Okay? So what this equation is telling you is that V depends on what medium you're in, right? And different wavelengths will then have different frequencies. If you fix the medium and you change the wavelength, right, what that means is you fixed V and you're changing lambda. Right? So in order for that equation to still hold, F must change. Everyone with me so far? Okay. Don't worry, it's difficult, we'll get through it. Let me unhide part of this question. Remember, in this question, right, it's not the boat that's moving. Right? Read the question. It says the boat is moored in place. Right? What's actually moving, of course, is the water under the boat. Right? There is a wave propagating. I have a fair number of responses. While I'm curious, I'm not going to check. Okay, so the formula we want to use is V is lambda times F, right? Essentially, I'm given a few numbers. Do I know V? Yes. How much is V? 5. Right? I am looking to find how long does it take the boat to go from the top of a crest to the bottom of a trough. Right? Top of a crest to a bottom of a trough, and I know the spacing between wave crests is 20 meters. What is that length? Lambda. So I know lambda. But am I being asked to find the time period? Yes or no? Very good. Half the time period. Top of a crest to the bottom of a trough is not a full period. Right? It's crest to crest or trough to trough. Right? Top of a crest to bottom of a trough is half the time period. Right? So you will find for this that the time period is 4 seconds. Correct? Right? So the time you are being asked to find is half of that. Is this making sense? Let's see. Good. Okay, now look at this, and this takes a little bit of getting used to. This is kind of how we're trying to represent a wave moving. Okay, so this is a wave as a function of position. Right? So that's different locations on the wave as you're looking at it as a function of position. Right? Now, the next slide, which is the question. Do not answer this till you really think about it. at which of the labeled points in the rope, right, at its equilibrium position, and moving upwards in the plus y direction. Okay, so you have 5 labeled points in the rope, right? So you're being asked, first off, at which points, right, along that rope is the rope in equilibrium? 2 points. Which 2 points along this rope is the rope in equilibrium? A and E, correct? Right? That's where it's not displaced from its midpoint, so it's at equilibrium. Now is the fun part. In which of these 2 points is it traveling? Is that position moving in the upward direction? So remember, this is one snapshot, right? Right? This is a snapshot at a particular instant of time, as that wave is traveling in that direction. Correct? I am asking you at which of those 2 points, right, A or E, is that point moving upwards? So now it's a snapshot, and let time go. Like, see that at that location, A or E, what is its next location? Right? Where is it going to go? Up or down? The point itself. Look at the rope at A and E. Those are the 2 points at equilibrium at some fixed time, right? Now advance time in your head, and this is the hard part. Right? Advance time in your head as the energy propagates through it. Right? It's going to displace that position. I want to know at which of those 2 locations is it going to displace the rope upwards, and, well, obviously the other one would be downwards. There's only one correct answer. And I'm going to actually close the question before I look at the answer. So take a Yep, that's wrong. And it's understandably wrong. This is confusing, but I love that you guys got that answer. Okay, let's analyze it. How do I get rid of this? Right. If I look at this wave, right, at this position, so these were my 2 positions, A and E. Everyone following me? The wave is propagating this way. Right? That means as time goes on, right, this part of the rope, right, its next location has to be here. This makes sense? This, you can think of this as an entire sinusoid moving. Right? So take that chunk and displace it slightly. Right? So if I take that position A and I displace it slightly, to the left of it, it's up. Does this make sense? Right? This part of the string is higher than this. Right? So this part of the string is being pulled up. Right? As this moves on in time, and I can draw it a little better, these are my 2 snapshots as a function of position. Right? This is my initial, right there. Everyone see that? Wow. I can barely see it, so there we go. Right. We identified this location and this location, right? Correct? At some instant in time. Right? So now the wave has moved this way. This makes sense? This is one instant in time. It's a picture of that wave on that string at a given instant in time. Right? Split second later, I take another picture. Right? The wave has moved that way. So now this becomes like that. Correct? You can see how this wave moved that way compared to that wave, right? Everyone with me? Does everyone see how this guy is offset in that direction compared to this guy? Right? So this part of the string is now over here. Right? So it moved up. This makes sense? If it helps, the first 5 times I did that question, I came up with E. Okay? Mentally, just looking at it quickly, for some reason, it flicks the other way. Right? You literally have to think of it as 2 pictures, one after the other, slightly offset. Everyone with me? Okay? It does require a little bit of visualization, which is not always easy. Okay, don't worry, I'm going to keep on this. Oops. Let's presume no one saw that. And tell me at which of the points along this oscillation is the rope instantaneously at rest. It's an oscillation, right? So for an oscillating mass, at which point in its oscillation is it instantaneously at rest? Have a mass oscillating, right? Where is it instantly at rest? Where does V go to 0? Where it turns, right? At either end. Where is that string turning? Right, click something. Very good. I'm going to presume that's not because you all saw the answer before. Right. Now, to actually see if we've understood this. Do the following. Talk to the person next to you. I should be hearing noise. I should also be seeing people's hands doing something like that. Don't thwack people, but talk to each other. And what you're doing when you're talking to each other, of course, is trying to convince each other that you're right. No one next to you, talk to the person behind you. That kind of works, okay? Okay, 5 seconds. Right, click something. Very good. Okay, it's not perfect, but I'll take it. right? When this wave moves, and the easiest way to see it is draw it out, right? When this wave moved from there to there, right, it's traveling in this direction. The next part is this, right? So this has to now be here, which is this, right? So if you look at this curve and this curve, this guy is ahead of this one by a factor of lambda over 4, right? Which is how much you travel in t over 4. Okay, very good. Oops. Right, it's the same kind of question, so it's up there and you can do it. Now, we've said a wave takes energy from one place to another, right? And a wave has a certain frequency and a wavelength and a speed determined by whatever media it's in, right? The question, of course, becomes how much energy does a wave take from one place to another, right? Does that depend on wavelength and frequency? So go back to oscillations, right? In an oscillation, simple harmonic motion, what determines how much energy is stored in the oscillation? I'm looking for that fill in the blank. What determines for an oscillation how much energy is in the oscillation? And this is stuff you need for Wednesday. Area, no. The spring constant, yes. So whatever is like trying to get this thing back to equilibrium, right? The elastic force involved, right? So yes, that does determine how much energy is in the oscillation. What else? Does frequency matter? For an oscillation, it doesn't, right? The mass of the string, but that's again in the same thing as k, as like how tight that media is. If I have an oscillation like this, right, about a point, and I compare it to an oscillation like this, which of these oscillations has more energy? This one or this one? The second one. So what's different? Amplitude. Remember that, right? The energy stored in a spring is 1/2 x squared, right? X being the displacement, right? This is essentially a springy system, right? So the energy stored in a wave is proportional to the square of the amplitude, right? It's how big that displacement from equilibrium is that determines how much energy is stored in a wave. Okay, just like it is the displacement from equilibrium, that amplitude, that determines how much energy is stored in the individual oscillation. Right? Intensity is a measure of power, which is energy over time divided by area, right? It's power over area. The best way to think of intensity is really, you can think of it as how loud I am. It depends on how close you are to me, right? The power I'm putting out, right, is the same, correct? But as that wave travels, sound is a wave which is traveling from me to you, right? Well, without the mic, it would be traveling from me to you. With the mic, it's traveling from multiple directions, right? But let's say without the mic, like now, right? It's traveling from me to you. Who thinks I'm getting? So people at the front, right? Correct? It's the same amount of energy that was dissipated out of me. And what happened to that energy is it got distributed over a larger and larger area. Right? So your eardrums have some finite size. So if you're up close, you're getting more energy hitting that eardrum. Right? If you're further back, right, you're getting less energy here hitting that eardrum. Right? That is the intensity. Right? It's the same effect for like a light bulb, right? You go up really close and stare at it, it's very bright. You start backing out, right? And the amount of light entering your eyes from it actually goes down. Right? A way to think about it is blowing up a balloon. Right? If you think of the power as the membrane of the balloon, right? As that balloon blows up, right? That membrane is getting thinner and thinner. This making sense? Because it is being divided by the entire surface area of that balloon, which is now getting larger. Right? Okay. So remember this, that the intensity of a wave is proportional to its amplitude. Right? Okay. And obviously, you can think of the intensity as a total power divided by the area it's spread out over. And the area it's spread out over is like a sphere. Right? Because it's going in all directions, three-dimensionally. Right? Which basically means it is literally like a basketball that's expanding. Right? So you're dividing that total power by the total area you're spreading it out over. Okay? Don't worry about the math. I will not be asking you math questions on this semester on intensity. Okay. Now we have a few minutes to study the velocity of a wave. Right? So V equals F lambda. Think about units. Frequency is 1 over seconds. Wavelength is meters. Speed is distance over time. So that's wavelength over time period, or wavelength multiplied by frequency, because 1 over time period is F. Right? So you'll get speed in meters per second, which should make sense. Right. So what we said is that the velocity depends on the medium. Right? It depends on what the wave is propagating in. Right? Because the amount of force, right? There is a certain restoring force, right? When a wave is propagating in a medium. Right? And that depends on how tightly that media is bound. Everyone with me? And you have actually studied numbers that describe how tightly different media are bound. Can anyone tell me what those numbers are? Which numbers do we use to describe how stretchy or bendy a material is? Which constants? This is also Wednesday's exam, by the way. The moduli, right? Young's modulus, bulk modulus, right? When you apply a stress to a material, how much it stretches and compresses, right, in response to that stress is the modulus. Correct? So as waves travel in different media, right, the speed of the wave in that media depends on the moduli of that medium. Right? I do not expect you guys to remember these equations, and you will not be needing to use them mathematically either. But look at the dependence. Right? So what we're saying is, look at the second one. B is the bulk modulus, right? Wave speed in a fluid. And as we'll see starting Monday, we can consider air to be a fluid. Right? Sound is a wave. Right? So the speed at which sound is propagating to you from me, right, is determined by how tightly bound air is. Right? How does the motion of one molecule of air affect the motions of other molecules of air that are next to it? Right? That property is the bulk modulus of air. Right? It's like how does air respond to a compressive or a volumetric stress? Correct? Right? So before you leave, just answer me this. Would you expect sound to travel faster in air or in water? And in order to answer that, what you want to think about is which of those two media, sound in air or sound in water, which of those two media is more tightly bound? Water, right? We all agree that water is more tightly bound than air. Correct? So in which case would you have more restoring force, water or air? Water. More restoring force means is the wave going